Okay. Starting. So, announcement form. The chapter 20 homework is due on Wednesday. Or the first part of the chapter 21 homework will be due on the 11th. The second part of the chapter 21 homework will be due on the 18th. We'll be doing a review of chapters 19 through 21 on the 16th. And we'll have the exam on chapters 19 through 21 on the 18th. We're probably going to finish chapter 21 by the beginning of next week, Monday next week. So we'll cover some more material before we have the review of the exam. Because I slightly miscalculated when scheduling stuff, but I don't want to move any due dates up. Okay. So we'll just have the exam a little later. Any questions about that? Okay. So we talked about current and power with in circuits. So let's talk about and we talked about resistors. So resistors, V equals IR for resistors. Now, if you have a group of resistors, you can have your resistors either be in series, like the circuit we made in the lab, circuit with no branches, or they can be in parallel. I heard a ding. Ah, okay. Let me. So resistors can either be in series or in parallel. So in series, when resistors are in series, that is, they're all lined up in a row like this, they all have the same current because they're in a loop. The current in a loop like this doesn't have anywhere to split to. So the electrons that are going through here have to then go through here and go through here and go through here. So the current is the same everywhere. You don't get a change in current unless there's a branching, splitting. So what you can do is that if they're in series, the equivalent resistance is equal to the sum of all the individual resistances. So it's, the sum of R sub I. So, R1 plus R2 plus R3 plus dot, dot, dot. So if you have three resistors in series like this, they will act like a single resistor with a resistance equal to their sum. So each one will have a voltage drop of V equals IR. The current is the same. So the voltage drop for all three will be as if it was R1 plus R2 plus R3. So when resistors are in series, they add. The equivalent resistor for resistors in series is R1 plus R2 plus R3 and so on. Now, we also have resistors in parallel. So because the current in these resistors, each series resistors needs to be the same, and the total potential difference is just the sum of the potential difference across each resistor, we find the equivalent resistance is just the sum. But resistors can also be in parallel. Here, when we have resistors in parallel, these wires are all connected by a conductor. So the voltage along the voltage difference here is the same for all the resistors. they have the same potential difference, but the current splits up. The current is the sum of the individual currents. So when they are in parallel, the equivalent resistance is 1 over the sum of 1 over the individual resistances, or 1 over R1 plus 1 over R2 was 1 over R3, or most commonly written something like 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3. So using the fact that the potential difference across each resistor is the same and the total current is the sum of the currents, we find 1 over the equivalent resistance is 1 over R1 plus 1 over R2 plus 1 over R3. So when you add up the inverses, you need, this is giving you the inverse of the resistance. So you have to do 1 over it. Is why I wrote it out like this. So just in general, rule of thumb, if you have a bunch of resistors in series, you're going to get a bigger resistance. If you have a bunch of resistors in parallel, you're going to get a smaller resistance. And then if a circuit is more complex, you start with combinations of resistors that are either purely series or in parallel, and then replace these with their equivalents. And then as you go on, you'll be able to replace more and more of them. So for example, in this more complicated circuit, you'll start by replacing these two resistors with their equivalent, which would be R over 2. And then we have 3 resistors in series that you can then replace with the equivalents. The whole thing will have an effective resistance of 2.5 R. So here we have 3 resistors connected in series to a 24-volt battery. The current in the circuit is 0.0466 amps. And resistance 1 is 225 ohms. Resistance 2 is 155 ohms. So find resistance 3, and then the voltage across each resistor. So here you need to find the equivalent resistance for the whole circuit by using the current and the total voltage. And then you can use the current and each individual resistor. Once you know the equivalent resistance, you can find R3. And once you know each individual resistance, you can use V equals IR to find each individual voltage. So I'll let you work on this for a little bit. So. and this goes parallel. So voltage is current plus our total resistance. Current times total resistance. V equals IR. We're just using this equation. So our total resistance is voltage divided by current. 24 volts divided by 0.0466 amps. Total voltage divided by current. That is 515 ohms. That total is R1 plus R2 plus R3. Just the sum of them, because they're in series. The 515 ohms is 225 ohms, that's R1, plus 155 ohms, that's R2, plus R3. And 515 minus 225 and 155 gives you 135 ohms. So R3 is 135 ohms. That's the missing resistor. If you want to find the voltage across each resistor, well, now we know R1 is 225 ohms, R2 is 155 ohms, and R3 is 135 ohms. So we can use V equals IR for each resistor. V1 is our current, 0.0466 amps, times R1, 225 ohms, which is 10.5 volts. V2 is current times R2, which is 0.0466 amps, times 155 ohms. V2 gives you 7.22 volts. V3 is, again, current times R3, so 0.0466 amps times 135 ohms, which is 6.29 volts. And if you add up all of these, you'll get 24 volts. So rounding errors. Any questions? Now here we have the same three resistors, but now in parallel. And we want to find out the total current supplied by the battery and the current through each resistor. So for that, here, each resistor is experiencing 24 volts. So the current for each resistor, we can do current is voltage divided by resistance and just divide 24 volts by the resistance of each one. And the total current will actually be the sum. But we can find the equivalent resistance first. So you can find the equivalent resistance for three resistors in parallel using this, and then find the total current supply. So I'll let you work on that for a little bit. let's go through this process. First, total resistance is 1 over R1 plus 1 over R2 plus 1 over R3. So that's 1 over 225 plus 1 over 155 plus 1 over 135, all to the minus 1, which is 0.018. This number in inverse ohms to the minus 1 gives us 54.6 ohms. That's our equivalent resistance. Voltage is total current divided by total resistance. So total current is voltage over total resistance. So 24 volts over 54.6 ohms gives us 0.439 amps. Now we can do each individual current and resistance. Find each individual current. Voltage equals current times resistance. Current equals voltage over resistance. So current 1 is going to be voltage over resistance 1. So 24 over 225, which is 0.107 amps. Current 2 is voltage over resistance 2, 24 over 155, which is 0.155 amps. Current 3 is voltage over resistance 3, 24 over 135, which is 0.178 amps. We add all these together, we will get the total we got in the previous part. So in parallel, current adds, voltage is the same across all of them. In series, voltage adds, current is the same for all of them. So in series, you add resistance. In parallel, you add the inverses of resistance to get the inverse of the total. And if you add these up together, you get 0.44 amps, which is basically what we got for our total. So we have two identical light bulbs that are connected to a battery, either in series or in parallel. When the bulbs are connected in series, are they brighter, dimmer, or the same as in parallel? Remember that energy, the output from a resistor, voltage squared over resistance. But more accurately, the brightness of the light bulb will be proportional to the voltage drop across it. So, you think that brighter, dimmer are the same in series as compared to parallel? Which one do you think is going to give you brighter light bulbs? Series or parallel? You have a guess? Think series is brighter? So power is current times voltage. And voltage is current times resistance. So power is voltage squared over resistance. The series splits the voltage up. So each bulb will get a portion of the voltage. If they're identical, each one will get half the voltage. Parallel, each will get the whole voltage. And you'll have more current flowing. You'll effectively have less resistance. So you'll have more. So parallel will have more voltage per bulb and thus more light. You'll have more current per bulb, more light. you could do it. We have sets of identical light bulbs. They will be quite a bit different. Because effectively, if you put them in series, each one gets half the voltage. When you put them in parallel, each one gets the full voltage. There are other reasons also to wire light bulbs in parallel. It means if one burns out, the other isn't affected. But that's specifically with a battery with constant voltage source. If you got a constant current source, then series would be better. So in the circuit below, EMF of the battery is 12 volts. So this is a 12-volt battery. And each of the resistors is 200 ohms. So what's the current supplied by the battery and the current through the lower two resistors? So remember, this you're going to have to work in parts. To find the total effective resistance, you'll find the effective resistance of the bottom and then of the top. And then so you'll have to combine these in series first and then combine the whole thing in parallel. So let's start by finding the current supplied by the battery. So we can go through this process. These two resistors here are in series. These will functionally have a resistance of 2R. Then this means we have R and 2R. So our total resistance is going to be 1 over R plus 1 over 2R to the minus 1. So because R is 200 ohms, this is going to be 200 ohms, 200 ohms. So this branch is 400 ohms. This is 200 ohms. So this will be 2/3 R just from that, but you could also plug in the numbers. So you can put in, this is 1 over 200 ohms plus 1 over 400 ohms, or -1. And that'll be 2/3 R, which is 133.3 repeating ohms. Our voltage is total current times total resistance. The total current is going to be our voltage of the battery divided by the total resistance. So 12 volts divided by 133.3 ohms is 0.09 amps. So there are 0.09 amps going through the whole circuit. And we want to find the current for the lower two resistors. Well, looking at this voltage difference is 12 volts, which means this voltage difference across these two resistors is also 12 volts. So the current at the bottom is going to be the voltage over 2R, 400 ohms. 12 volts over 400 ohms gives you 0.03 amps. And if you calculate the voltage on the top, that's 0.06 amps. And they add up to 0.9. Any questions? Okay. So here we have two circuits with the same batteries and the same resistors, but slightly different arrangements. So which of these two circuits has the higher current? I.e., which of these two circuits has the lower resistance? So here we have one resistor in series with two resistors in parallel. And here we have one resistor in parallel with two resistors in series. So which of these do you think ends up with the higher current, i.e. the lower resistance? Yep. So here, the resistance will be at least R. It's actually going to be 1.5 R. But here we have R here, and then some additional path that it can take over here. This will be, the resistance will end up being, because this is 2R and this is R, and then the whole thing will end up being 2/3 R. Let me just see if I work these out. Okay, I'll work it out. So over here, we'll end up with resistance total is going to be R plus 1 over R plus R, which is 1.5 R. Because this will be 1/2 of R, and then they add. So current is voltage over 1.5 R. Well, over here, this is 1 over, our total is 1 over R plus 1 over R plus R, which comes out to 2/3 R. And current because this is 2R, and then they're in parallel. Current ends up being voltage over 2/3 R, so this is 2/3 V over R, and this is 3/2 over R. So this has the higher current, this has the higher resistance. Basically, the way you think about this has to go for at least one resistor, which is going to slow it down. This splits, and so it has multiple paths. Or the other thing is just generally, when you have some things in parallel, you get a smaller resistance. When you have things in series, you have a larger resistance. So the base here is series with a resistance of R, so it'll be bigger than that. The base here is parallel with one of the resistors being R, so it'll be less than that. But yes, circuit 2 has the lower resistance and the larger current. So sometimes you get more complicated circuits that you can't nicely break down into series and parallel pieces. And for these, we use Kirchhoff's rules. And Kirchhoff's rules are really just really basic. They're just ways to formalize for circuits, really basic facts about the universe. That they each correspond to conservation laws, actually. So Kirchhoff's rules, there are two rules for Kirchhoff's rules. There is the junction rule and the loop rule. The junction rule is a consequence of charge conservation, and the loop rule is a consequence of energy conservation. So here are Kirchhoff's rules. The junction rule says basically what goes in must come out at a junction. The current entering a junction must equal the current leaving it. Or if you talk about, if you add up the current entering a junction, so here I1 is going in, I2 and I3 are going out, so they're negative. You add up all the currents entering a junction, they have to add up to 0. So I1 is going in, I2 and I3 are going out, so I1 minus I2 minus I3 must equal 0. That's the junction rule. Fairly straightforward. What goes in must come out. The loop rule says if you go around the loop and add up all the potential differences, they have to add up to 0. Because if you had a net potential difference around the loop, you could build up energy. But if you go around the loop, once you get back to your start, energy should be conserved. So energy should be the same. So all the potential differences should add up to 0. So here is the simplest case. You have a battery, which creates a potential difference, and you have a resistor, which creates a negative potential difference, and they add up to 0. For the loop rule, you have to pay attention to how you're going around the loop. As you're going around the loop, for a battery, when you go from minus to plus, that's a positive potential difference. When you go with the current through a resistor, it's a drop. It's a voltage drop. So this would be written out as, if you're going around the loop this way, and the current I is going that way, as shown in the picture, this would be written as epsilon minus IR equals 0. So there, if your loop is going in the same direction as your current, that you've defined as your current I. Resistors cause a negative potential difference, and batteries going from minus to plus in the direction of your loop are positive. If they're the other way around, they're negative. So using Kirchhoff's rules, the variables you're solving for are the currents through the resistors. So you'll have a set of currents. And you need as many independent equations as you have variables to solve for. And you will always need both loop and junction rules. So usually you need like one junction and enough loops to solve for enough variables, or it depends. But you always need both loop and junction rules. You cannot do it with only one or the other. Here we have this loop here, loop 3. Let's write the equation for loop 3 here. I'm going to erase this resistor info. So as we go around, we would start with the battery. We're going from minus to plus as we follow the loop around. So we have epsilon. Current 1 here has nothing. Current 2 here has a resistance of I. So we have minus I2R. Then we're back to current 1 over here. That also has a resistance of I. So minus I1R equals 0. So here, as you go around the loop, voltage of loop 3 equals 0, which is epsilon minus I2R minus I1R. So here we have another more complicated one. Let's go through and we can write the equations for this. So we have 2 loops and 2 junctions. We could have a third loop if we wanted, but let's use the 2 loops they've defined. And then junction A. So let's write the equation for loop 1. So going around the loop 1 with 15 volts. Then current 3 is in the same direction as the loop. So we have minus I3 times 100 ohms. And then we have current 1 here, minus I1 times 100 ohms. We can do loop 2 over here. So loop 2, here we're going from plus to minus on the battery. So that is minus 9 volts. Because the direction of our loop is opposite the direction of this battery. We're going from plus to minus on the battery. Then here, current 2 is going in the same direction as the loop. So we have minus current 2 times 100 ohms. And then over here, current 3 is labeled as going opposite the direction of the loop. You can think of it as negative. So minus minus I3 times 100 ohms, or just plus I3 times 100 ohms. But because I3 is going opposite the direction of the loop, it's negative. So you can think of it as minus minus. Which, and then this, oh, this equals 0, and this equals 0. And so we can rewrite this as 0 minus 9 volts minus I2 times 100 ohms plus I3 times 100 ohms. And then our last equation is a junction equation. Let's do at A. So at junction A, 0 is going to be I1 minus I2 minus I3. Let's see what I actually did for the write-up. So the voltage of loop 1, 15 volts minus I3 times 100 ohms minus I1 times 100 ohms. Voltage of loop 2, negative 9 volts minus I2 times 100 ohms plus I3 times 100 ohms. And IA is I1 minus I2 minus I3. So now we have a system of equations that we can solve to find the currents. So the easy way is you stick this in a matrix and then we'll reduce it or something. Yeah. We write it as a matrix, minus 100. So this is I1, I2, I3, and then equals voltage. So minus 100 times I1 minus 100 times I3 equals minus 15 volts. Minus 100 times I2 plus 100 times I3 equals 9 volts. And I1 minus I2 minus I3 equals 0. If you row reduce it, you find I1 equals 0.07, I2 equals minus 0.01, and I3 equals 0.08. So I1 equals 0.07 amps, I2 equals 0.01 amps, and I3 equals 0.08 amps. I mean, you can just go through and solve the system of equations however you want. Plugging it into a matrix and using row reduction is probably just the fastest way to do it on a calculator. So here we want to state Kirchhoff's rules, the loop equations for loop 1 and loop 2. Well, loop 1 has a plus 12 volts minus I3 times 200 ohms minus I1 times 300 ohms. And loop 2 has minus 9 volts minus 150 ohms times I2 plus 200 ohms times I3. So 0 equals 12 volts minus I3 times 200 ohms minus I1 times 300 ohms. 12 volts minus I3 times 200 minus I1 times 300. And VL2 minus 9 volts minus I2 times 150, and then plus I3. That's a typo. Oops. Okay. And that's a misplay. But, plus I 3 times 200. Any questions about Kirchhoff's rules? On tests, I'm not going to ask you to solve systems of equations because it just takes too long. I mean, there's going to be homework for it, but on tests, I'm just going to ask you right now. So I think that's actually where I want to stop for today. We will continue on Wednesday. Just a reminder for people who got here a little late. Let me pull up the announcements. Chapter 20 homework is due on the 24th. Chapter 21. Desktop. Sharing. Yeah. Oh well. Whatever.